Electrons tend to move in this state, depleting some of this state in the negative k direction, and then causing some of the states in the positive k direction to be occupied. And if that is the case, then there will be more electrons with this kind of positive momentum compared to electrons with this kind of negative momentum, and there's net movement of the electrons across the crystal lattice. Okay. And that is the picture that you should have of electron conduction. And you can say the same thing on holes too. Okay, in holes, then you can argue that some of the holes might move about because of that, and you might have some of this being depleted. And if they're depleted, then you can actually have some holes that have maybe more momentum or more momentum in that direction, and some with more momentum in that direction. And then you will have a net movement of holes. Okay? But the theory of holes is actually quite complicated. It's not that simple as we say. If you want to actually understand how holes move about in the crystal lattice, you essentially have to study the field theory of solid states in order to understand how those holes interact with the background. But in a simple-minded picture, you can think of them as this way. Okay? So I'd like to move on to a topic which I feel is very important. Which is the effective mass Schrodinger equation. So we have this crystal lattice that we say we have a block locate mode moving about this crystal lattice. The block locate mode looks something like this. In 1D, it looks something like this. In 3D, it might look something like this. Okay? So we can ask ourselves, what happens if k is very small? Then we will have a very long wave, a slowly varying wave, modulated by a rapidly varying function that has to satisfy the boundary condition of the crystal lattice. Could we describe this with a simpler picture? Okay, this electron is moving about in this periodic lattice with this wave function. Can we find a simpler picture for this electron to move about? And that is the idea of the effective mass picture. And this is extremely important for semiconductor physics, or compound semiconductor physics as well, because in there we always talk about electrons moving in the lattice. We never talk about electrons moving in the vacuum. In electrical engineering, very rarely do we think about electron moving in the vacuum. Okay. Electron is always moving in the lattice, and when that electron is moving in the lattice, can we have a simpler picture for that electron? Let's derive that simpler picture. And if we notice that after all the band diagram studies, we end up with band diagrams that looks like this. Okay. And we say that E of k can be approximated with a parabola that looks something like this, plus V. Okay. If I call this value V, I can always approximate the band diagram by that parabola when k is small. Okay, when k is small, I can approximate that band diagram as such, and ask myself, can I derive a simpler equation? Okay, and this can happen in 1D, 2D, or 3D as well. Then I ask myself, the wave function that I should have that propagates through this crystal lattice must be a sum of the block locate modes that are possible. Okay, the sum of the block locate modes. Each of these block locate mode will look something like this. Okay, this is my EFM, the block locate mode, or block locate wave. And then they will have different K values. Okay, they will have different K values. And then each of them will have a different energy level, E sub K. Okay, each of them will have a different E sub K. And that E sub K has a corresponding omega. Okay, I can think of that H bar omega K is E sub K in this picture. Okay? That is the description of the Schrodinger wave propagating through the crystal lattice in terms of the block locate modes. And I ask myself if I can simplify this picture, especially when I'm in the long wavelength limit. When the wavelength of K corresponding to K is so long that I can make approximations. Okay? And if I look at the equation for K, again, if you remember what that equation is, in one dimension we had something that looks like this. If I write that equation down again, okay. The equation for K was something like h squared over 2m minus k squared UPX plus 2ik UP prime x plus UP double prime x plus VP x UPX is equal to EX or something is equal to E UPX. Okay, so when K goes to 0, I can ignore this term. I can say that UK of R is approximately equal to U0 of R when K tends to 0. So in the long wavelength limit, I can approximate the periodic part of the function with the periodic function at K equal to 0. Okay, by just staring at this equation. If K is very small, the solution for K not equal to 0 is very similar to the solution for K equal to 0. Can everybody see that? Okay, if that is the case, then I can say that this can be made to be independent of K. I will approximate UK of R with U0 of R. And take this out of the equation and say that this must be a very rapidly varying function. Okay, very rapidly varying function independent of K times UK dot R minus I omega KT. This must be a slowly varying function. Because K is small. A slowly varying function of R. Okay. So in the long wavelength limit, I can think of the block locate mode as being expressible in something much simpler, or the Schrodinger wave function can be approximated with just this function times an envelope function. Okay? The envelope function that I have here is just equal to ck equal to ik dot r minus I omega kt. Okay? So if I ask myself, what kind of equation does this envelope function satisfy? I can differentiate it. I can let the time derivative operator operate on it. Then if I were to take it inside, I would have something like minus I, actually it would just be h bar omega k e to the I k dot r minus I omega kt. Okay, and this h bar omega k is just e sub k. And e sub k, as I said before, can be approximated somewhat. Where did I say the approximation? I guess I erased it. E sub k can be approximated in this picture. E sub k is just equal to h squared all this here. Okay? E sub k can be approximated by that. So I can substitute that back in and say that this is equal to c sub k h squared k squared over 2me plus b e to the I k dot r minus I omega kt. Okay. Now I can take this thing and replace that k squared with something else, with an operator. Okay? I can say that this is h squared Laplacian squared over 2me plus b. Okay? Then if I do that, I can take this outside and say that this is h squared Laplacian squared over 2me plus b, operating on the function that remains behind. That function that remains behind is just size of e of rt. So I can see that the envelope function satisfies this equation that looks like Schrodinger equation, or exactly like Schrodinger equation, except that I have an effective mass and I have an effective potential. Okay? How does the effective mass comes about? It comes from curve fitting. You fit your curve so that this parabola is been fitted by this parabola. You pick the v so that it is the bottommost level of your band diagram. So after you have done the band structure calculation, you can take the value of v and the curve to be the mass. Okay? And that is called the effective mass Schrodinger wave equation. Okay? So effective mass Schrodinger, EMS. Okay? Are there any questions regarding this? Because it's a number that I put in, a number that I pick up from this band diagram. It's the number at the bottom value of this conduction band. I call that number V in my effective mass Schrodinger equation. Okay? Do the band structure calculation. I find the value at the bottom of the conduction band. That value is called V. And that makes this look exactly like the Schrodinger equation you have learned in the beginning of class. This looks like the Schrodinger equation for an electron traveling through vacuum. But this electron is not traveling through vacuum. It's traveling through a crystal lattice. And it has this effective mass and this effective potential. Okay, there's a picture you should have. So this actually is what governs semiconductor physics. Most of semiconductor physics is done with this Schrodinger equation, not the one for an electron traveling through vacuum. Okay, so this is a very important equation for you. But you have to bear in mind that this is only an approximate picture. It's not an exact picture. Okay? And you use that equation to derive much understanding about semiconductor physics in electrical engineering. Okay? You stop here and you lecture again next Tuesday at 9 a.m. And this afternoon I'll give you a take home. I hope it's an easy one. Okay? I think it's rather easy, so I just give